Good morning, everyone. Good morning. Hope all is well. Hope everyone's doing all right. Got good morning. Good morning. Got one or two still trying to connect. So let's give them a few seconds. All right. So today we're getting into chapter 5, into a little probability. Starts off with what is randomness. So people are not good at identifying true random samples or random experiments. So we need to rely on outside mechanisms such as coin flips or random number tables in order to identify for that for us. So random means that no predictable pattern occurs and that no digit is more likely to appear than any other. Everybody done with the black? So probability is used to measure how often random events occur. Example of that, there's a 50% chance that a coin will land on tails. Still holding on to red. All right, theoretical probabilities are long run relative frequencies. It is the relative frequency at which an event happens after infinitely many repetitions. So that's why it's theoretical, because we're talking about infinitely many times that the experiment or event has been run. Still not. Am I still holding on to theoretical? Okay. So when we say a coin has a 50% chance of coming up tails, we mean that if it were possible to flip a coin infinitely many times, then exactly 50% of the flips would be tails. And that means 50% of the flips would also be heads. All right, empirical probabilities are short run relative frequencies based on an experiment. So if you toss the coin 10 times and you get 7 tails, your empirical probability of getting tails is 7/10, which is 70%. So you can see the difference. There's a big difference between your empirical probability and your theoretical probability. Empirical is based on the actual experiment that you've done, the actual outcomes and observations that you obtain. But theoretical is based on theory and is based on infinitely many times that the actual experiment is run. Everybody done with the black? So the empirical probability tells us how often an event occurred in an actual set of experiments. Theoretical probabilities are based on theory and tells us how many times an event would occur. And I'll give you a chance right before I scroll all the way up. And so once again, theoretical probability is based on infinitely, the experiment being ran infinitely amount of times. All right, simulations. Simulations are experiments used to produce empirical probabilities. Investigators use them with the hope that their experiments simulate the situation they are examining. No simulations. So green statement, example of that, one could use a computer program to simulate flipping a coin 100 times. So of course you don't want to have to flip a coin 100 times in order to get to see what would happen if you flip a coin 100 times. So you can use a computer program to simulate or have a simulation that does that. Anyway, holding on to the purple. All right. So theoretical probability measures the proportion of times events would occur if an experiment is repeated infinitely many times. This means it is impossible to carry out this task. It's impossible to do something infinite amount of times. So we can use empirical probability to estimate and to test the theoretical probability. All right. So if I want to just setting us up foundation for how we're supposed to be thinking about probability, theoretical, empirical. 5.2 is where we actually get into calculating it. So when you go into 5.1 homework, it should be stuff like this, worded stuff like this, that they'll be asking you what's theoretical, empirical probability and stuff like that. So before we go into 5.2, is everybody okay with copying? Can I scroll up? All right. So 5.2, finding theoretical probabilities. Is everybody good with that last statement of 5.1? All right. So an experiment is any process with uncertain results that can be repeated. So an example of that is flipping a coin. Sample space is going to be all possible outcomes of an experiment. So if you're talking about flipping a coin, all possible outcomes of flipping a coin would be heads and tails. Then an event is any collection of outcomes from the sample space. So if we want to know the probability of landing tails, then tails would be our event. Are we done with sample space? Okay. So the complement is going to be all outcomes in the sample space that are not the event. So in this case, if we're talking about the probability of tails, the complement of tails will be heads. So all the outcomes in the sample space that are not the event. All right. So the notation for the complement, if our event is E, then that C with the superscript, or that E with the superscript C would be the complement of the event. So you'll have a C that would just be like an exponent up to the right. So in this, just saying here that if you had event A, complement of A would be A with that C up as a power. All right, everybody okay? So summary of probability rules. Rule 1 is that your probability is always in between, always between 0 and 1, inclusive. So that means it is possible to have 0% chance, or 1, which would be 100% chance, but it's normally in between 0 and 1. Hold on to notation. And then rule 2, three different ways of looking at the probability and the relationship between the probability of an event and the probability of the event's complement. So if you have the complement, if you subtract it from 1, that will be the probability of the event. If you have the probability of the event, if you subtract that from 1, that will be the probability of the complement. Or if you just add the probability of your event and the probability of the complement of your event, they will add up to give you 1. So like I said, all of this is just very different variations of the same relationship. So the probability of the complement is 1 minus the probability of the event. So it's just, like I said, it's just a variation of the same relationship. Mhm. So rule 3, the number of outcomes in your event over the number in your sample space will be the way you calculate your probability. All right, so let's say we want to find the probability of landing tails. Most of you already know it's 50% landing, 50% chance of landing tails. But the way you want to do it is you always want to find your sample space first. What is the number of outcomes in your sample space? So we see here that it's just heads and tails. So the number of outcomes in our sample space is 2. Then the event is landing tails. So there's only one way to land tails. So the number of outcomes in that event is 1. Once you have the number of outcomes in your sample space and then the number of outcomes in your event, you place the number of outcomes in your event over the number of outcomes in your sample space. And that'll be 1/2, which is 50% if you convert it to a decimal. Any questions? Any questions? I'll scroll up. Everybody okay? Okay. Next example, we have a 10 dice. I say a 10 dice. We have 10 dice in a bowl. We're going to reach into the bowl that has 5 red dice, 3 green dice, 2 white dice. What is the probability of picking a red die? Then what's the probability of getting a green die? Then last, what's the probability of getting a white die? All right. So let's look at the red die first. First thing we need to do is establish our sample space, and that is 10. Add up all our dice together. 5 plus 3 plus 2 give us 10. So you always want to establish your sample space first, no matter what probability you're dealing with. Then from there, we have 5 red dice. So if I want to know the probability of getting a red die, it's 5 out of 10, which is 50% chance. All right, questions on the red die? All right, so looking at the green die, same thought process. Once again, the sample space is what you would establish first. And it's the same as what we just finished doing. We haven't changed problems. So our sample space is still 10. Then there's 3 green die. So we put 3 over 10. So we got 3 out of 10. Chance of getting a green die. Then the same process for the white die. Sample space is 10. There are 2 white dice. So place the 2 over 10, that'll be 1 over 5. Any questions? All right, scrolling up, everybody good? All right, so this time we have 2 dice, and we want to roll the 2 dice and add the outcomes. So what is the probability that the sum of the 2 dice is 7? So this time we're looking at the numbers, or sometimes they're called pips, on the dice, on the face of the dice. So it's a little different than what we were doing before. Before we were just looking at the color of the die, color of the dice. Are we dealing with that last problem? Okay. So once again, we want to establish our sample space. Now our sample space is based on the numbers that's going to appear on the dice after we roll them. So, you know, when we're talking about sample space, we're talking about all the possible number combinations that can be created. Talking about with die 1 being 1, die 2 being 1, die 1 being 1, then die 2 being 2, then 1, 3, 1, 4, then all those combinations. And then you're talking about die 1 being 2, then 2, 1, 2, 2, 2, 2, 3, 2, 4, and all those combinations as well. So if you haven't dealt with dice before, haven't dealt with them in a while, you know, our faces look like this is 1 through 6, you know, and those little dots are called pips. So, you know, 1, 2, we have 2 that represents 2, 3 represents number 3, and so on. So we have 1 through 6 for each die. Now, we can use the fundamental counting principle instead of trying to list out all of these combinations and possibly missing 1 or 2 or just having a long process. Because of the fundamental counting principle, what we can do is recognize that die 1 has 6 faces, and then die 2 has 6 faces. And then we can just multiply those together. And that gives me 36. So that's 36 possible outcomes when you're looking at 2 die or 2 dice that have 6 faces. Now, let's say if Math Lab give you, I don't think they will, but they give you a crazy scenario in which one die has 6 faces and the other die has 10 faces. Then it would be 6 times 10, which would be 60 combinations or 60 possible outcomes. Or if it was one die had 6 and the other had 8. 6 times 8 would be 48 possible outcomes. So you just multiply the total number of outcomes for each die together, and then that'll give you your sample space. All right. So everybody okay with having 36 as a total number of possible outcomes when we roll 2 dice? Okay. So we want to find the probability of rolling a 7. So we have to explore all of the ways that we can get 7 when we roll these dice. So everybody okay? Can scroll up, scroll up. Very good. Okay, here. So we're talking about die 1 being 1, die 2 being 6. 1 plus 6 gives me 7. Then we have 2 and 5, and then 3 and 4. Now, die 1 being 3 and die 2 being 4 is not the same as die 1 being 4 and die 2 being 3. So then we have to, explore 4, 3, 5, 2, and then 6, 1. So we have 6 possible ways of rolling a 7. That's the number of our event. All right. So once you have that, you just do 6 over 36, which reduces down to 1 over 6. All right. Very good. So here we have a chart that you guys are going to have to copy. Well, you don't have to copy, but we're going to reference. So the education represents education and marital status for 665 randomly selected U.S. residents. So let me erase some of these boxes. All right. So education level is the first column. So there's less high school, then college or higher. And then your totals, then you got single, married, divorced, widowed, and then total there. So I'll give you a chance to copy that down. He said the formula to find probability. I can show it to you, just give everybody a chance to copy this chart before I scroll all the way back up. But it's the probability, well, the way to find it is the number of your event over the number of your sample space. All right, are we done copying? Can I scroll up? All right, so you're talking about way back here. This is it right here. Oh, and I have my eraser on. This is it right here. Number of outcomes in your event over the number of outcomes in your sample space. Yep, no problem, no problem. Everybody good? All right, so let's look at this chart and see how it's going to help us in this next example. Suppose we select at random from the collection of 665 people. I see 65 is the total number of people altogether that we have. So that's going to be our sample space number. What is the probability that the person is married? All right, so like I said, our bottom number is going to be 665. That's the total number of people that we have altogether. And we are looking, what's the probability that the person is married? So that would be this number right here. The total number of people that are married is 408. So that's just going to be 408 over 665. And probably went this far with it because that's probably what MathLab asked for, or at least the example in the book gave me. So MathLab could ask for a fraction, decimal, or percentage. Just make sure you pay attention to what they're asking of you as far as that is concerned. But that's A. All right. Everybody okay with A? All right. So what's the probability that the person has college education or higher? So you would go to college education or higher, the total number of people that have college education or higher. It's 143. If I'm not mistaken, we're going to use this chart again and do other things with it. So make sure you have a place. Well, I guess you could copy it again when we go there, but so here, college education or higher. So 143 over 665 would be 21.5%. So what's the probability that a person is married and has a college education or higher? So bottom number is still 65, but he said married and college education or higher. So that's right here. It's not just married, because just married would be the 408. That's all the people that's married. This time we're looking at married and college education or higher. So that's 98. And so 98 over 665. And so whenever you see the word and, it consists of only those outcomes that are both events. So both of our events, he was married and college education or higher. All right. All right. So you have the word or consists of all outcomes that are in A, that are in B, and that are in both. All right. Write down the green statement. So what is the probability that a person is single or married? So let's see, we're not going back. Yeah, we are going back to the chart. Okay. So what's the probability that a person is single or married? So just referencing the Venn diagram, I believe they did so in the book. We're talking about circle A, that's your event A, circle B being your event B. And then the red shaded is both. So we're talking about that would be your and. Now, or is going to be all of each circle. So you're talking about adding the green, red, and purple together. That's what or represents. Like I said, and is just represented by the red shading, or is represented by all three of those shadings. So everything that's in B circle, everything that's in A circle are added together. And that's what or represents. All right, so let's go back to our question. What's the probability the person is single or married? So we're looking at 665 as our sample space. Now let's go back to our chart. So we're talking about being single or married. So I need the total number of single people, total number of married people. Eventually, we're going to look at what if they had things in common. These two categories, it's impossible to be single and married at the same time, unless you got entanglements, right? But it's impossible to be single and married at the same time under normal circumstances. So we would just take the 112 and the 408 and add them together. Somebody caught that. So add them together, and that'll give us 520. And place that over 665, and that'll be your percentage. So like I said, though, we'll look at when you do have something in common, how you would operate. But right now, we're looking at two different categories. They have nothing in common. All you would do is add those totals together, and that is your top number. Oh, okay, the next one is like that. Okay, well, we'll look at that next. All right. Next one, what is the probability the person is married or has a college degree? All right. So now we have two options of how to explore this event number for us. The last one, like I mentioned, it's impossible to be single and married at the same time under normal circumstances. So they had nothing in common. But here it is possible to be married and have a college degree. And what you don't want to do is to count certain numbers twice. All right, so let's go back to our chart. So this category represents the married people. This category represents all of the people that have a college degree. So if you notice in this category, 98, or in these categories, if I were to just add up 143 and 408, I would be counting 98 twice, because 98 is a part of the 408 number. 98 is a part of the 143 number. So what I could do is just add up the numbers that I see, 27, 70, 240, 98, not the 408, that's your total, 15 and 3. So I can just add up those numbers. And that's what I did. Where we at? Right here. So you add up those numbers and that gives you 453. So you add up each individual piece, or you can add up the totals and subtract the number that they have in common, which is 98, and that'll still give you 453. So it's up to you. Doesn't matter which way you decide to view it. Just make sure on this top, when you're not adding the total's not a part of that calculation. You add up each individual piece or each individual category. So that was a 70, 240, 98, 27, 15, and a 3. That gives you 453. Or you can add up the two totals and just subtract the one that they have in common, which was at 98. And you still get your 453. All right, questions on that? Scrolling up a little bit to finish the problem. So once you have that 453, place it over to 665, 68.1%. All right. Yep, I would think so. But it always depends on how you see it at that moment. And a lot of times math, what dictates what's the easiest is your mindset when you go in. Some people, it may be easy just to add the pieces together. So, so I'm just giving you your options. Yep. All right, are we good to scroll up? Body okay? Hold on, let me see how much more is left out of this section. Yep, just this one example. Okay, yep. So we'll finish this off and then be in a good place. So mutually exclusive events. So events that do not have any outcomes in common. So that references being single and married. So it is impossible for these events to happen at the same time. So once again, under normal circumstances, being single and being married are mutually exclusive events. All right, so rule 4, This leans on what we did in that last example. If your events are not mutually exclusive, then you would add the two probabilities together, subtract what they have in common. But if they are mutually exclusive, all you do is add your probabilities together because they don't have anything in common. So that's basically those last two examples, what we did. The first one was mutually exclusive events. That's why all we did was add the two probabilities together. The second one had something in common, that 98. So that's why we added the probabilities together and then subtracted. Well, in that case, it was just the numbers, but we can still apply it to our probabilities as well. So. All right, scrolling up. So we roll a fair six-sided die. Find a probability that the die shows an even number or a number greater than 2. I still holding on to black. All right, so I'm going to label E for even number, G for the event greater than 2. And I'm going to find my probabilities individually first. So our sample space is 6, 1 through 6, 1, 2, 3, 4, 5, 6. Now my even numbers within that sample space is 2, 4, and 6. So I have three numbers that are even. So that's why my event is 3. And then 3 over 6 is going to be that probability. I'm not going to reduce this yet. I'm going to reduce at the very end. It's best to go ahead and leave your fractions intact the way they are. Because when you talk about adding fractions, subtracting fractions, maybe you need a common denominator. But if I reduce this down to 1/2, reduce it to 2/3, I'm going to have to take them back to a denominator that has the denominator of 6, which would be what they originally have. So it's best to reduce your fractions at the very end after you've done all your calculation. So I'm going to leave that as 3 over 6. And then here, the numbers that are greater than 2, 3, 4, 5, 6. So I have 4 numbers that are greater than 2, so that'll be 4 over 6. And I'm going to leave that the way it is as well. All right, everybody good with that? So are these events mutually exclusive? The answer is no, because they have 4 and 6 in common. So they're not mutually exclusive. Mutually exclusive means that they do not have anything in common, like being single and being married. But these events have 4 and 6 in common. So we have to explore that piece as well. So we're talking about being even and greater than 2. We already know it's 2 numbers that fit that description. Is everybody doing with the purple and green? So that's going to be 4 and 6, which is 2 numbers that fit that description of being even and greater than 2. So that's 2 over 6. I don't know what I was doing over here to the right. So it must have been something that somebody had asked specifically in a class. So go ahead and erase that so nobody copies it down for no reason. So now we have even and greater than 2 is 2/6. All right. So now finding the probability of E or G being even or greater than 2. Take the probability of being even plus the probability of being greater than 2 minus the probability of being even and greater than 2. So that's 3/6 plus 4/6 minus 2/6. And that'll give us 5/6 as our probability. All right, any problems? Next one, still looking at our die. Find the probability that the die shows an even number or the number 5 on top. All right. So sample space, once again, is 6. We're dealing with this single die. Even numbers that we have, 2, 4, and 6. So it's 3 of those numbers. So the probability of getting an even number is 3/6. Now the next event, it says the probability that a number 5 appears. So the probability that a 5 occurs is only one way that can happen. If 5 shows up. So the number of that event is 1 because there's only one 5. And so that probability is 1/6. All right. So now, are these events mutually exclusive? The answer is yes. They don't have any outcomes in common. And you can always go back to your listing if you're not sure. You're only 2, 4, and 6. Here we're talking about the number 5. So they don't have anything in common. So this means we can just add the probabilities together. Everybody holding on to purple and green? All right. So probability of E plus the probability of F. 3/6 plus 1/6 is 4/6. And that'll give us 2/3 once we finish it off. All right, any questions, any questions? Okay, so That's it for 5.1 and 5.2. See, next we have 5.3. So I'll pause right here. So before we close out today, everybody good? Everybody straight?
Can I talk to you after class?
Sure.
I appreciate it.
All right. So if everybody good, I'm good. Have a great weekend. Be safe. And we will pick back up here on next class. Take care.
Thank you.
Thanks, you the same. Take care. Let me stop.